Hey, good morning, YouTube, and Happy New Year. Stephen Fleet here. Hey, I wanted to build upon some of the previous videos I made about basically rediscover a Dirichlet series, 3x plus z, where z is this equation, and it ends up alternating between plus 2 plus 1 plus 2 plus 1. And y will first give you 5, then 7, 11. It'll give you all the prime numbers. It won't skip any prime numbers. It'll give you all the prime numbers, but it also gives you semi-primes, say like 25 and 35, and then also some composites. It'll end up giving you 25 squared, then 25 times 9, and 25 times 31. And similar with all these values, it'll give you 5 squared, then 5 times 7, 5 times 11, and then 7 squared, and 7 times 11, and 7 times 13, and so on. Now, the important part here is that this Dirichlet series, there's a pattern in the semi-primes and composites that it produces. You can actually tie an equation to the different semi-primes. So when you look at, let's say, all the square values, 5 squared, then 7 squared, and 11 squared, it has specific x values that go into it. And so there's an equation that actually governs these. And then same thing when you multiply it, say 5 times 7 or 7 times 11. And so there's a whole nother series of equations. Now, I'll go through that here in a second. So 5 times 7, x would be equal to 11. So that would be the 5 times 7. This would probably be, so 25. That should end up being 7 times 11. So yeah. But I'll quickly jump ahead. I know it's a bit of a hodgepodge here, but takeaway here is that you can predict semi-primes and composites in the Dirichlet series, and you can do it with these formulas. And in this case, when I was first doing this, I used y of 1, y of 2, y of 3, but you really have to envision y of 1 of actually just being x of 1 in this equation. So the y value here would actually be the x value here. We'll strike through this notation, and a little bit later, we'll just switch to the g equals 3y plus z. So that way the y value here is the y value here. And z is the same thing, same part. So if we start a new integer series, n goes from, say, 1 to infinity. Y would equal 8 in this case. Y of 2, we'll say n equals 1, y2 equals 11. Right here, n of 1, we'll say y of 3 equals 18, y of 4 equals 21, and so on. So you have all specific n1 values. Now what ends up happening is that you're alternating between this equation and this equation. So y of 2 is the same thing as y of 4. Instead of adding y of 1 into it, you're adding y of 3. And y of 5 is the same exact equation as y of 3, but instead of adding y of 2, you're adding y of 4. So you're adding the one from previous. And so, you can go all the way to infinity if you want. And you can envision this as, you can put this into matrices where you're creating all these y values, and then this is for n equals 1, and then you can say this is for n equals 2. Each n value is a column. And so you can create a matrices of x values, and I'll say y values in this case. It was x, but it goes in here of these y values that will predict all of your semi-primes and also your composites that are predicted by the Dirichlet series. Now, what's important here is that you can then get all the prime values by exclusion. So where all the semi-primes and composites are. So wherever they are not is where there's a prime value. You can actually get that through interpolation if you wanted to. Where, if you have, say, your first y of t here was 8, and your second y of t was, say, 16, and you have a t value that goes from 0 to 1, so basically you kind of scale it, you could then get a y value that is, say, 9 or 10 and 11 and 12 and 13. And you can do that down a column, across a row. You can do that diagonally between 8 and 25. So the Dirichlet series, what I initially called y equals 3x plus z, now we're going to say it's g equals 3y plus z, where y or these individual equations, this will give you all of your semi-primes and your composites. And you turn that into a matrix. And all the values, all the integer values in between these will give you the primes. And as a last example, say I choose 9. So maybe, so when this creates, one of these formulas will create, say, an 8. And if I interpolate it to where now my y value would equal 9, it would go right, you get a 9 between here, 9 between here, 9 between here. When you plug that 9 into here, your g value will give you a prime. So takeaway here is that you can predict prime numbers. You can predict prime numbers. And you predict them by essentially not predicting them. They're the ones that are left over in the Dirichlet series, out of this series of equations here. And that's important because, number one, you're never really going to be able to predict a prime number by an ultra simple, clean formula, just because prime numbers depend on everything before it, and then ultimately, as it continues to build, all the numbers after it, and especially all the factors for the integers before it. So you're always going to have some sort of formula that's either recursive or goes off towards infinity, you name it. But this is probably the cleanest way. You can even turn this into a primality test if you want to. You could even add like a Heaviside function, Dirac delta. You can do all sorts of different indicator functions to where it'll clean it up. And that way it's maybe even a little easier to follow or test. But the takeaway here is that you can predict prime numbers. And it's simply a matter of interpolating the integers between your matrices. So, hope that helps. Yeah, thank you.